Hello everyone! In this video we will continue to examine topic D.3 cosmology, and in particular we will continue to examine the Big Bang model, Hubble's law, and redshift. So, returning to this idea, we can then define Big Bang, or the Big Bang, as a cosmological model, that is a model of the history of the universe, of the observable universe, from the earliest known periods through its large-scale evolution. And important aspects of the Big Bang model, now articulated or currently articulated, but stemming from this initial discovery of Hubble's law, is that the Big Bang is the formation of time and space. So time and space began at the Big Bang. It makes no sense on this particular model to ask what was before the Big Bang. And in part, this particular constraint, which sort of boggles the mind and confuses us, is in part due to the connection between time and space we discover in relativity. So relativity suggests that space-time can be viewed as part of the same structure. And so, although we're slightly more comfortable with space beginning at a certain point in time, usually it bothers us more that time would as well. But we just bite the bullet and say, where did the Big Bang come from? I don't know. Physics does not offer a causal explanation to that. But after that, it's more straightforward. We say that space has expanded to its present point in time, and it has been about 13.8 billion years ago. We will discuss more how we came up with that estimate a little bit later, but the general idea is, as I said, with Hubble's law, if you just run the movie backwards, where does it begin? And that gives you an estimate of the age of the universe. Notice it began there, or at that point in time, every place in space. Every place in space was closer together. Every object in space was closer together. And as a result, it didn't happen in a particular location. It happened everywhere all at once. What does it mean for space to expand? What does it expand into? Is a common question. Is a little bit challenging. What we say is that the fabric or background of space expands. So the galaxies become farther apart without themselves moving. Now, from our perspective, we can't tell the difference directly between a galaxy moving away from us and there being more space in between us. We can't detect the difference. They look the same directly. But mathematically, we actually have a very clear distinction between the two. In Einstein's field equation, which you'll not be asked to use, in part because it uses tensors, which is beyond us, there is a very clear difference between the space-time terms over here and the stress-energy tensor over here. This is the stuff. And as we've discussed before in mentioning general relativity, mass bends space-time. So mass energy bends space-time, and then space-time influences how mass and energy respond to it. So if space-time is bent, then it controls what it is for things to move in a straight line, for example, along a geodesic. So it's important to note that these are two distinct mathematical terms in the equation, and here's the important difference. The velocity of objects is in this term on the right. But when space expands, it can be detected or quantified in these terms on the left. So there's a mathematical difference in the way we analyze the expansion of space and mass energy and the movement of mass energy. And what this means is that even though we cannot directly detect this difference, we can quantify what we might expect if space-time were to expand versus what it would be for objects to move, and then we can go look for it. And as it turns out, if space-time expands uniformly, we see exactly what we would expect given Hubble's law. So we have a way of quantifying it, and a way of saying, here's what the evidence would be. So we go look for the evidence, and we find it. Note, it is not expanding into anything. It's just that the matter itself is farther apart. So the analogy for this that is quite common is to imagine sort of dots on a balloon. So you draw dots on a balloon, and you consider the universe as like the surface of the balloon. The dots are so far apart. Then you blow up the balloon, and you'll discover that as you blow up the balloon, the surface of the balloon, notice, is not expanding into anything. There's just more space on the surface, and all the points on the balloon, on the surface of the balloon, get farther and farther apart. Now notice the balloon itself is expanding in the third dimension, but here the matter in the space of 3 dimensions is not itself expanding into anything. Everything is just getting farther and farther apart. And so the galaxies have a redshift as if they were moving apart, even if they were not. As a result, if I scoot back here a little bit, even though we defined redshift initially with respect to the Doppler effect is due to velocity. And so in retrospect, we need to be really careful about how we describe the redshift of galaxies, because if it is due, in fact, to this expansion of space, it is known as the cosmological redshift, it's not actually because the galaxies themselves are moving. So in Hubble's initial characterization of this, he said, oh, well, the further away they are, the faster they're moving. But a better description of it would be the further away from are, the faster they appear to be moving away from us due to the expansion of space. So it's the expansion of space that leads to that redshift. In order to quantify that expansion, we can define what is known as the scale factor, r. Okay, and the scale factor r is a function of time, so it depends on time, but it's equal to the physical distance at any point in time divided by the coordinate distance. So let's have an idea of what that means. Imagine this little number line represents space. At this point in time, at point A, these two dots are exactly 2 apart. So in the coordinate system, if you just lay a coordinate grid over their space, you'll see that they are exactly 2 apart. But as space expands, they get farther apart. So D prime, that's the physical distance, they are now farther apart than they used to be. That's due to the expansion of space. But the coordinates stay the same. So the coordinates here sort of capture where the space is. That's the way to think about it. And so the scale factor is the ratio of where of what the physical distance is compared to what it was before. And how do we know what it was before? We quantify it using a coordinate system. The scale factor right now would be 1, because the space right now relative to our current coordinate system would be 1. Later on, as space expands, we would expect that scale factor to get bigger. And if we run the movie backwards, we would expect that scale factor to be smaller relative to our current coordinate system right now. Notice, this is the same thing that happens with light. So if a photon of emitted wavelength travels through space, then you would expect that wavelength to expand as well. And so this phenomenon is known as the cosmological redshift. And in fact, that's our explanation for why things are redshifted. So why do the galaxies have a redshift as if they were moving apart? Well, as time goes on, that wavelength, okay, lambda, stretches. And so the light is stretched, or the electromagnetic waves are stretched as the space itself stretches. This can be shown here. If the emitted wavelength is lambda 0 is equal to the scale factor when the photon is emitted times delta x, that coordinate distance, then it is, notice what we're doing here is we're plugging lambda 0 in for d. Then it is detected at a new wavelength, lambda, which is equal to the scale factor, whatever it is, times that coordinate distance. And so we take the two ratios of that, and we discover that lambda over lambda naught, so the detected wavelength divided by the emitted wavelength, is equal to the ratio of the scale factors here. As a result, the redshift can be directly quantifiably related to the wavelength and to the scale factor. So the redshift defined to be lambda minus lambda 0 over lambda naught is equal, this can be shown with algebra, to the ratio of the current scale factor divided by the original scale factor or the emitted scale factor minus 1. And this equation captures the relationship between the redshift and the scale factor. If you measure the redshift at any point, you can measure what the scale factor was at that time. That's r. So as the universe expands, the wavelength of a photon emitted in the distant past increases when measured at the present time. It's not that they just become red, so this incorrect picture depicts the Doppler effect, but what is actually happening is that the wavelength is stretched over time.